Okay. Next, we have this AES, which is called Advanced Encryption Standard, because with the time, as the time passed, so advancement in machines was also introduced, and there were machines which I told you in the previous class as well that it took only few hours to crack the code which was encrypted using DES. Okay, but when DES was introduced at that time, machines were not capable of doing this. But with time and the advancement in machines which was introduced, it became possible. So that is why the idea of using some other algorithm which is more secure, it was arised. Right. So again in 1997 NIST, it started looking for a replacement of DES, and that replacement it called as AES, which is Advanced Encryption Standard. Okay, so this is again a symmetric key block cipher which was published by NIST, because NIST, it was looking for proposals, and in 1997 it started looking for the proposals from various people. So the idea or the requirement behind looking for some other algorithm, it included some specifications. So the specifications, main specifications was the block size was supposed to be 128 bits, and it said that the algorithm should use different key sizes. Okay, different as in it was required by NIST that the key sizes should be 128 bits, 192 bits, and 256 bits. Okay, and it also required that this AES should be an open algorithm which could be used by the public. Okay, so with these specifications, NIST it started looking for the replacement of DES. So initially, in the first round, 21 algorithms was received, and out of those 21 algorithms, 15 algorithms were shortlisted. Then in second round, out of those 15, only 5 algorithms were shortlisted. Okay, and these 5 algorithms were Mars, RC6, Raindoll, Serpent, and Twofish. Then in 2000, out of these 5 algorithm, this rain doll algorithm, it emerged as winner, and it was introduced as AES. Right. So this algorithm then it was published by this FIPS, which published DES as well. So it was actually published in December 2001. So that was that was the history of AES. Right now we will be discussing the criteria which NIST wanted in AES. Right, so there were three criterias which are this first one is security, then the cost, and then the implementation. So under security, they wanted actually the security was the main point which NIST wanted, and that is obvious. They were looking for some cryptographic algorithm, so security is must. So for security, this NIST they wanted 128-bit key, and the use of or the demand of 128-bit key was specifically for resisting the algorithm for cryptanalysis attacks, right, other than the brute force attack, because with the advancement in the machines, the brute force attack became possible up to some extent. Okay, so that is why this use of 128-bit key was a must. The second one is cost. So the second criteria was cost, which covered the computational efficiency and storage requirement for different implementations like hardware, software, and other things. Then the third thing was implementation. So this requirement, it included the all the requirements that the algorithm, uh, it must have flexibility so that it can be implemented on any of the available platform. Okay, and the simplicity was also required. Okay, so these are the three criterias over which this algorithm, which was the Randall algorithm, it was accepted for AES, right? Then next we have rounds in AES. So AES is a non-feasible cipher which encrypts and decrypts a data block of 128 bits. Okay, which was the basic requirement. Data block should be of 128 bits, and the key also should be of 128 bit or more. And this algorithm, it used 10, 12 and 14 rounds, and depending on the number of rounds, number of different sorry depending on the number of rounds, key of different sizes were used. So for if the algorithm used 10 rounds, then the key size was 128 bits. If it used 12 rounds, then the key size was 192 bits. And if it used 14 rounds, then the key size was 256 bits. Okay, which depends on the number of rounds. So that is the same thing written over here. Okay, three versions were there with these three number of rounds, and these three number of rounds, they use this much of key bits for the encryption process. Okay, but the size of round key is always 128 bit key. So if you remember in DES as well, the size of cipher key was 56 bits, but the size of round key was 48 bit, right? So here as well, initially we could have this much of key size, 128 bit or 192 bit or 256 bit. But while generating the round key, the size which we use for key is only 128 bit. Okay, so that we have to keep in our mind, right? So this is the general design of AES encryption cipher. So we can see from here that this NR, it defines the number of rounds, right? And it shows the relationship between the number of rounds and the key size. Okay, this is the table which shows you the relationship between the number of rounds and the cipher key size. So as I have already told you, if we use 10 rounds, we use key size of 128 bit. With 12, we use 192 bit. With 14, we use 256 bit of cipher key. Okay, round key will be always of 128 bit key. Okay, so here it is also written cipher key. You can see we use three kind of keys or three sizes of key, and the round key is always 128 bit, right? And the number of keys we use is always one more than the number of rounds. So here if NR is the number of rounds, this is the number of round. Okay, you can see that we are starting from K0 and going up to KNR. So the number of key will be always plus 1 to the number of rounds. And in this, the first step for this 128-bit plain text, we have some pre-round transformation of the data. Then we go through multiple number of rounds, which depends that कौन सा कितने number of rounds हम लोग use कर रहे हैं यहाँ पे. And then we get the 128-bit cipher text, right? So this is the general design of AES, wherein we deal with 128 bit of plain text, which we encrypt using number of rounds, and for each round a different key we will use, and the size of key will be 128 bits, right? So That is the general design. Then comes the data units which we use in AES, okay, because we need to deal with the 128 bit of data. So we have a number of units with us which we can use to deal with the data. So the smallest unit we have is bit, okay. So bit can represent a value which is 0 or 1. And to represent a bit, we use the lowercase letter which is B, okay. And when we write this B in bold, then we are representing byte, okay. So after bit we have byte. So byte is what? A byte is a group of 8 bits that can be treated as a single entity. We can treat it as a row matrix which is of 1 by 8 size, or a column matrix which is of size 8 by 1, right? So when we treat it as a row matrix, then the values are inserted from left to right. And when we consider it as a column matrix, then the values are inserted from top to bottom. Then after byte comes the next unit comes is word, which we represent as W, okay, in lowercase. This is again in lowercase. Byte is again in lowercase but in bold. Fine. So word is what? It is a group of 32 bits that can be treated as a single entity. So we can treat it as a row matrix of 4 bytes as well, or a column matrix of 4 bytes. So same thing will apply over here. If we consider it as row matrix, then the values will be inserted from left to right. If we consider it as column matrix, then the values will be inserted from top to bottom. Fine. Next unit we have is block, right? First we had bit, then byte, then word, and then block. And the size of these units is increasing. Fine. So block is, block is the thing which we use in AES, right? And a block is a group of 128 bits, or you can say it is a group of 4 words. So 4 words you can see over here, or 128 bits you can say. So, or 16 bytes also we can call them, okay. So it can be represented as a row matrix of 16 bytes. Fine. So this is how we represent it. Next we have is state. So AES uses several rounds in which each round is made up of several stages. जैसे हमने जो previously जो structure किया है इसका, we have a number of rounds over here, and each round is made up of a number of stages that we will discuss in the coming slides, कि कैसे हम लोग राउंड को यूज करते हैं, राउंड के अंदर क्या क्या स्टेप्स होते हैं, कौन कौन सी स्टेजेस होती हैं, right? So each round is made up of several stages, and the data block is transformed from one stage to another. We have, say for example, we have 4 stages in one round, and we input the data into that round, and that data goes through a number of stages wherein the data is transformed from one form to another form at each and every stage. So at the beginning and end of the cipher, AES uses the term data block. So whenever the data will enter over here, from here, we call it data block. And when it exits the whole structure, we call it data block. So here and here, we call the data, we use the term data block. Okay. And inside the rounds, we inside the rounds and here as well, when the data moves from here to here, and when it's come out from here to here, we call it data block. But inside the round, when it moves from one stage to another stage, then the data block is referred to as state. So inside the round, we call that data block as state. Fine. And outside the round, whenever it is entering a particular round or exiting a particular round, we call it data block. and we use this uppercase bold letter, which is S. So this will be always written in bold and will be in uppercase to represent the state, right? So this is the fourth data unit which we are discussing, whose name is state, right? And for instead of using this S, which is written as capital and in bold, we occasionally write it as the letter T for for referring to a temporary state, right? But we generally make use of this S. Now the states, like the block data unit, these are made up of 16 bytes. Okay, 16 bytes. We can check it from here because this is using 4 words. So block is always using 4 words or 16 bytes. So state is always state is also made up of 16 bytes. But normally these bytes are treated as matrices of 4 by 4 bytes. Okay, and we represent this state just like a matrix of 4 by 4. Here we are using a row matrix, but to represent state we use this 4 by 4 matrix, right? So at the beginning of the cipher, the bytes in the data block are inserted into the state column by column and in each column from top to bottom. So how do we insert data in this state? How do we represent the data using a state? So we will be inserting it just like this, which is represented over here. So we will start inserting the data column by column and top to bottom. Okay, and we represent each entry in this matrix as this thing. So this is what? This is S, R, and the subscript is R and C. R represent the row and C represents the column. Fine. So this entry will be for 0th row and 0th column. Okay, so we will start inserting the data from here, from the first column and from top to bottom, and then we move to the second column, then we fill the data from top to bottom. So this is how we fill the data into a state, right? So we can change this block to this state by inserting the data in this format, right? And the format will be equivalent for the extraction as well when we extract the data from the state. Okay, so this matrix form can be converted into a block by extracting the data into the same fashion in which we have inserted it, right? So this is the fourth data unit which we use in AES, which is called as state. So inside round, whenever we deal with the block of the data, we call it as state. Okay, so that is the example of changing the plain text to state. So here and what we have done is this is the text with us. AES uses a matrix. Okay, then the size of this matrix is 4 by 4. So these two bogus characters are inserted over here. So यहाँ पे हम लोग hexadecimal data का use कर रहे हैं. So we will use the same notation from 0 to 25 for each and every alphabet, and then we convert it into hexadecimal representation, and then we will insert all these values into a form of matrix by inserting them column by column and top to bottom. So this is how we represent the given text into a state. Fine. Next comes the structure of each round at the encryption site. So this given diagram, it shows you the overall structure of a round, right? So here we can see that each round that this thing we have to keep in our mind, that each round except the last round, it uses 4 transformations. So for transformation it uses, this is sub byte, shift row, mix columns and add round key. Okay, and the last round does not use all the four transformations, right? And the the third transformation is missing in the last round. So this transformation is not there in the last round. Fine. And we can see from the diagram that each transformation, it takes a state as the input. So from here we can see it takes the state from the input as the input, and it performs some transformation. We will discuss these transformation steps in detail after this topic. So but right now we have to understand the structure of round. Okay, so it takes the state as input, performs some transformations and gives you another state as the output, right? Then this state, which is the output of first transformation, goes into the second transformation process. Then it again generates the output in the form of state, right? And then this goes into next level of transformation. It again outputs the data in the form of state. Then again it goes to the fourth transformation, and then we have the data in the form of state, right? So this is how this round works. And one more thing, before the first round we do not use all of these transformations. We only use this add round key transformation. Okay, this is the point written over here. So before the first round we only use this transformation, and for the last round only three transformations are used: 1, 2 and 3. So this mix column is missing in the last round, and in the first, before the first round, only this is used, right? So this is the structure of each round at the encryption side of the of the whole process. Thing I was telling you, that these four main transformation steps we have, or these are the type of transformation which we apply to the plain text to get the ciphertext, right? So we will be discussing all of them one by one. So first we will start discussing this substitution, or which we represent as sub bytes, right? So what does it say? AES, just like DES, it uses the substitution. Okay, we have used this substitution in DES as well, wherein we substituted, we made use of a number of S boxes, right? So AES uses two invertible transformations. These two invertible transformations AES uses, one is at the encrypting end and another is at the decrypting end. So the transformation which we use at the encrypting end is called subbytes. Okay, and the transformation which we use corresponding to this transformation operation we use at the decrypting end is called inverse subbyte, and that is represented using INV sub bytes, right? So the first transformation sub bytes is used at the encryption side. To substitute a byte, we interpret the byte as two hexadecimal digits. So we will be representing every byte in the state. So you have to keep in your mind now that we are dealing with the state, which is a 4 by 4 matrix, right? So we are dealing with the 16 bytes now. Fine. So while while applying this transformation step, while performing this substitution operation, we'll be dealing with one byte at a time, and we will consider that byte as two hexadecimal digits, right? So that is the same thing. This sub byte operation involves 16 independent byte to byte transformation. Why? Because we have this 4 by 4 matrix which we call as state, in which there are 16 entries. So there will be 16 independent byte to byte transformation. Each and every byte in this state will be transformed independently. Okay, and how do we do that? We will be converting each byte of that state as two hexadecimal digits, right? And the left digit of that hexadecimal number which we which we have used over here, which we have converted our byte into, the left digit will define the row and the right digit will define the column of the substitution table. So we will be having a substitution table. Uh, Actually, in AES, we have two substitution tables. One table will be used at the encrypting end and another table will be used at the decrypting end. So the first table we will be using for the encryption purpose, okay, or for the substitution at the encrypting end, and the second table we will be using for the inverse substitution at the decrypting end, right? So what we do is we will be taking the left digit of this hexadecimal digit uh, uh, as to find out the row of that table, and the right digit to find out the column of the substitution table, and then the two hexadecimal digits at the intersecting point of that particular row and the column will be our new byte. So I'll tell you with the example that how do we do this. So this is the state we have, and we are right now dealing with this particular byte. Okay, we'll be having 16 independent byte to byte transformations. So this byte is we have changed it into hexadecimal representation. So that is AB. Okay, now A is the left part, or the left digit of this number, or this byte, and this is the right part. So the left part will tell you the row of the substitution table, and the right part will tell you the column of the substitution table. Now the entry which is at their intersecting point will be the substituting byte. Okay, so in the result, this particular byte will be used. So this A and B will be replaced with C and D. Okay, I'll show you all these things with the table as well. How do we perform it? The process is same जैसे हमने DES में किया था, right? So say for example, I have this hexadecimal number with me, which is say 7 and 9, right? So 7 will give you the row number and 9 will give you the column number. So you will move along the 7 up to 9, right? So here we have reached. So B6 will be the substitution for 79, right? So this is how we substitute each and every byte of the state, and as a result we get a new state, right? Then at the decrypting end, we use the table which is there for the reverse substitution process. Okay, the process which we call as inverse sub bytes. Okay, so this it will be the inverse of sub byte operation which we have just performed, and it is used at the decrypting end. The table which we use for inverse of this substitution operation at the decrypting end is this one, right? So here we can see that this 79 was changed to B6. Okay, so this inverse table will be inversing that operation. So if we check for B6, we can check it from here, B, and this is 6. So if we go along this row, yes, up to here, and this column, so we get 79. Okay, so the process which the sub byte operation or transformation has done is reversed or inversed by this inverse sub byte operation at the decrypting end, right? This is how we use these tables for performing the first transformation step in each round. Now we also have another method of implementing this transformation step, of implementing the substitution operation, which we call as okay, this is okay. We'll be discussing that another method later. So that is the example, which is for a sub-byte transformation, which is the first transformation step in every round. So this example shows that how a state is transformed using a sub-byte transformation, and it also shows you that inverse sub-byte transformation creates the original one. Okay, and if the two bytes have the same values, then their transformation is also the same. So here we can see that this is 19, this is 19, this is 12, 12. So all the same entries in this state will be having the same substitution. Okay, so this 12 is being replaced by the same byte, right? Here this 19 is being replaced by D4. Fine. Why is it so? Because we are using a single table for it, right? So we can check for some of the entries in it. Say for example, if I want to check for 04 and I am performing this sub byte operation, so I have to check for this in table 1. The number was 04. Okay, this is 0, this is 4. Okay, so this is F2. So here we have F2 with us. Okay, and if we inverse it, if we perform inverse sub-byte operation, then F2 will give you F is here and 2 is here, right? So we reach at this entry. So this is 04. So you will get the original value, right? Which is 04. Okay. So that is the one method of implementing this substitution. Another method we have is transformation using Galois field. Okay, in this what we do is we simply we transform the given state, or we substitute each and every byte in the given state using these fields. Okay, and there is a proper way of doing it. So how we do this, we use this irreducible polynomial for finding out the modulus in this Galois field, Galois field, which is 2 raised to 8 field, right? So the sub byte and the inverse sub byte transformations are inverses of each other. So that is for sure कि चाहे हम tables का use करें, or if we want to go with these Galois fields, the sub byte operation or the transformation and inverse sub byte operation will be inverses of each other, right? So how do we use it? This operation we use we make use of these Galois field according to this process, which is shown in this diagram. So what we have is this sub-byte transformation using Galois field. It repeats a routine which we call as sub-byte, right? And that routine is repeated 16 times, again once for each and every byte in the state. And the inverse subbyte repeats a routine which we call as inverse subbyte, and each iteration transform one byte at a time. So that is why we repeat it 16 times. In the subbyte routine, which means at the encrypting end. Okay, when I say that subbyte, that means I am talking about the encrypting end. When I say inverse subbyte, then I am talking about the decrypting end. So in the subbyte routine, the multiplicative inverse of the byte is found in this Galois field with the irreducible polynomial, which is given over here. Okay, this one. So our first step will be finding out the inverse of the given byte, the byte which we are dealing at that particular time, right? So first we will be finding out the inverse, right? Then the inverted byte is interpreted as a column matrix with the least significant bit at the top and the most significant bit at the bottom. So this byte will be converted into a matrix form, okay, like this. The least significant bit will be at the top and the most will be at the bottom, right? Then what do we do? Then this column matrix, this byte which we have changed into a column matrix, is multiplied by a constant square matrix X, which is predefined. Okay, this is constant square matrix. So this column matrix which we have made out of this inversed byte will be multiplied. We represent it as X. So this X and the B, which is the column matrix, we multiply them, okay, and as a result we get another column matrix which we call as C, right? Then this resultant column matrix is added to a constant column matrix again. So this is one more constant column matrix we have. This is constant square matrix, this is constant column matrix. So this output which we are getting over here after this multiplication operation, we will add this this matrix, this column matrix, with this constant column matrix, right? And then we get another column matrix which we represent as D. Now this column matrix we will convert it into the form of byte, right? And then our process is done for the for the sub byte part, right? So this process will be followed for each and every byte of the state, right? Now while inversing it, or while dealing with the same state at the inverting end, the process will be reversed. So here at the decrypting end, instead of using addition, we will be using subtraction, okay, because the inverse of addition is subtraction, right? So the process will be reversed. So first we will be subtracting it, this D and Y, and then we will be multiplying the result with the inverse of this constant square matrix. Okay, यहाँ पे हमने x का use किया है, so here we'll be using the inverse of the matrix, and as a result we get the B matrix, B column matrix. Then we convert it into byte and then we inverse it, okay, and then we get the original entry for the state, okay, for the original entry for that particular byte which we have encrypted over here in the state. Okay, this is how this process works. So the inverse sub byte will be doing the same thing in reverse order. Fine. So this whole process can be represented using expressions which are like this. So at sub byte, what we are doing is we are inversing the byte. First of all, we are finding its multiplicative inverse, okay, which is the first step, finding out its inverse. Then what we are doing, we are multiplying it with the square matrix, the constant square matrix over here, which is the second step. Then we are adding it to the Y, which is the constant column matrix. Now here we have used this XOR operation. Why? Because we are making use of Galois field and we are making use of addition and subtraction, both of the operation. Okay, so in Galois field 2, the addition and subtraction, they both these operations are similar. So that is why we have used this XOR operation, right? So that is the process which is followed at the subbyte end or the encrypting end. Then in inverse subbyte, what we do is we perform the XOR operation of D and Y first of all over here, right? Then we multiply the result with the inverse of the matrix at this step. Fine. and then we find the inverse of the whole result. Okay, this is the inverse, so that is the same thing. We convert it into byte and then we find out the inverse, right? So we can check that whether the message or the state which we have encrypted and the state which we have got after decryption are similar or not. So we can change this these expressions into some other expression and we can find it out. So if we replace this d with this expression, so this will be the whole expression now. This d has been replaced with this expression, right? So these two entries will be discarded, right? Because we are performing this XOR operation, and this is inverse and this is X, so they will be cancelled and we are left with the inverse of the state, right? And again its inverse is done. So the inverse of inverse is the original number, right? So we are left with the original entry of the state. Fine. So this is how we transform or we perform the sub-byte operation or the substitution operation using Galois field. So this is just an example given over here, which shows that this byte is transformed into this byte by sub-byte routine and transformed back to this byte by the inverse sub-byte routine. So we will follow the same process. What we do is first of all find the multiplicative inverse of the given byte, okay, which is this one. So the value of byte we have is this one. Okay, we can represent this hexadecimal number into this number, right? Then we multiply this matrix X, which is the constant square matrix, with this value and we get this column matrix. Okay, then we perform the XOR operation and we get the final value for the encryption side, okay, which is FE in hexadecimal. Now at the decrypting end the process will be reversed. So the XOR operation will be giving you this value, then you multiply this thing with the inverse of matrix and you get this hexadecimal number, and when you find the multiplicative inverse of this, the result will be the original byte, right? So this is how it works. Okay, next step or the next transformation unit we have in each round is permutation, right? So I'll show you the initial diagram. So we are done with this substitution. Okay, now we are in this permutation. Okay, so we are now discussing this second step or the second transformation operation, which is permutation. So permutation may what we do is we perform the shifting operation, right? And again we will be discussing the operation which is performed at the encrypting side and the operation which is performed at the decrypting side. So the operation which we perform at the decrypting side, we represent it as inverse shift row, which we write as INV shift rows. Okay, in the first transformation we used inverse sub byte. Here the operation is shift row, so the inverse operation will be inverse shift row. So in the encryption the transformation is called shift rows. And how do we shift the rows? That is represented over here, right? So we will be dealing with state again. Okay, in this step, while performing this transformation step, we will not be dealing with one byte at a time, we will be dealing with one row at a time. Okay, so we will be dealing with 4 bytes at a time. So depending on the number of row which you are dealing, the number of shifts will be decided. So for row 0, no shifts will be done. That means 0 shifts will be there. For row 0, no shifts will be there. For row 1, 1 byte shift will be there. For row 2, 2 byte shift will be there. For row 3, 3 byte shift will be there. So this row, for this row there will be no shift. For this row there will be 1 byte shift. इसके लिए 2 byte shift होगा और इसके लिए 3 byte shift होगा. Okay, so depending on the number of row we define the number of shifts, right? And when we talk about shift rows, that means the permutation at the encrypting end, then the shift is left shift. Okay, and when we talk about inverse shift rows, that means the permutation at the decrypting end, that means then the shifting will be right shift. Okay, why? Because we have to reverse the operation which we have done at the encrypting end. Okay, so encrypting end पे हमने left shift किया, and at the decrypting end we will be doing the right shift. So that is the same thing. This operation is used at the decrypting end, and the transformation is called the inverse shift row, and the shifting is to the right. So this is the example of shifting and inverse shifting, right? So when we have this state with us, which is having 16 bytes, and we'll be dealing with one row at a time. So while performing this shift row operation, what we do is we'll be shifting this row with 0 bytes, right? This will be shifted 1 byte, this will be 2 byte, and this will be 3 bytes. So you can see over here the bytes which are being shifted are highlighted. Okay, so after 1 byte shift, this first row becomes this one. After 2 byte shift, this second row becomes of this form. This third row becomes of this form, right? Now that is the encryption side story. Now at the decrypting end, we will be performing this inverse shift row operation. So what we'll do is this row 0 will be, there will be no shifting. This row 1 will be shifted right by 1 byte. This row 2 will be shifted right by 2 bytes, and this row 3 will be shifted right by 3 bytes. So as a result, we get the original state, right? This is how we perform the permutation operation. So now we are done with two transformation operation in each round. The first one was substitution, and the second one is permutation. And now we have to discuss this mixing operation and the add key operation. Right, so that we will be discussing in the next class.